Every time you press a key, you are performing a mechanical action. A plastic switch bottoms out, forcing two metal plates to make electrical contact. This contact generates a voltage spike that travels down a copper wire. To the internal hardware, this electrical pulse is the only information that exists. Digital hardware is defined by the physical behavior of its transistors. These microscopic switches are designed to exist in one of two states, an energized on or a dormant off. This is the foundation of base 2 binary. This creates a gap between human thought and machine execution. How can a device limited to two physical states process the infinite variations of human language, mathematics, and imagery? Bridging this gap requires encoding schemes. These are mathematical protocols that map symbolic human meaning, like the letter A, directly to specific electronic patterns. Numbering systems such as base 2, base 8, and base 16 are not just academic concepts. They are the structural frameworks that allow software to communicate with hardware. To understand the digital world, we must look at how engineers translate complex human instructions into sequences of on and off pulses. We can observe this translation pipeline by using the word data as a test subject. Computers handle text through standardized dictionaries, the most common being ASCII. This protocol assigns a unique numerical code to 128 different English characters, numbers, and symbols. Under the ASCII standard, the letter D maps to the decimal value 68, A maps to 65, and T maps to 84. Because hardware processes electricity rather than decimals, we must convert the number 68 into base 2 binary. By dividing 68 by 2 and recording the remainders in reverse, we derive the 7-bit sequence 1000100. Repeating this math for every character reveals the underlying reality of digital storage. Words are represented as specific strings of electronic signals. Binary capacity is tied to bit depth. Adding just one bit to a sequence doubles the number of unique values it can represent. By moving from ASCII's 7-bit strings to the 8-bit ISCI format, engineers increased the character limit from 128 to 256, allowing for the inclusion of Indian script alphabets. This logic scales into Unicode. Using variable bit lengths, Unicode creates a global dictionary that contains a unique code for every character and symbol in existence, from ancient scripts to modern emojis. Text encoding provides the universal dictionary that dictates which physical transistors must fire to represent any given character. While binary is efficient for hardware, it is unmanageable for people. As software grows in complexity, raw binary strings become too long for an engineer to read or debug accurately. Identifying a single error in a 16-bit memory address like this is cognitively demanding. Hexadecimal and octal function as organizational layers. They allow humans to view and manipulate binary data without changing the hardware's underlying logic. Hexadecimal, or base 16, works because 16 is exactly 2 to the 4th power. This mathematical alignment allows us to group any long binary sequence into uniform blocks of 4 digits. We can translate the first block, 1100, into the decimal 12. Since base 16 uses single characters for values up to 15, the decimal 12 is represented by the letter C. Converting the remaining blocks reveals the compressed code. This shorthand reduces a cluttered 16-bit string into 4 clear characters, C0, F1. Octal, or base 8, follows a similar logic by grouping bits into sets of 3. Both systems provide a way to organize binary data into more readable structures. These numbering systems act as a visual shorthand, allowing humans to manage billions of active transistors without becoming lost in raw binary noise. We can see these layers in action by looking at how a computer renders color. Screens use the RGB color model, mixing red, green, and blue light channels. Each channel is controlled by a decimal value between 0 and 255. To produce pure yellow, a pixel sets red to 255, green to 255, and blue to 0. To activate the hardware, these decimals are converted into 3 8-bit binary strings. This 24-bit sequence represents the physical voltage commands for a single pixel. Instead of typing these long binary strings, web developers use hexadecimal shorthand to define colors. The 24 bits group into clusters of 4, resulting in the standard hex code FFF00. A programmer writes these 6 characters, and the compiler unpacks them into the 24 hardware switches needed to fire the pixel. Every digital experience is the result of this interconnected system: physical pulses given meaning by ASCII, organized by hexadecimal, and routed to hardware to render the modern world we see. The relationship between base 2, 8, and 16 is the mechanism that allows human intention to be executed by silicon. It is the core logic that makes modern computing possible.